Thank you, sir. Now I will request Professor Harish Hirani to start his lecture.
Thank you, Kundan, for this opportunity and morning inauguration time. Sri Singh has already paved the way that we really require some bearing technology which can speak its own, that I am at the fault, please change me. Or there should be a communication from bearing itself. That's what we are thinking about smart bearings. And I believe that AMB is kind of smart bearing. Bearing can tell exactly what is the problem and how to correct also. That's a possibility. So this my first slide shows the two books what Kundan has mentioned already. First book which I wrote in 2016 and an Indian edition also came in 2017. And second, because I have now more IPRs compared to my publication. So around 30 IPRs I have described in this book with a couple of real society purpose at why, and maybe we have developed a couple of technologies during COVID time. So today's topic what has been given to me is something like a magnetic bearing technology and application in industry. And thanks to Prof Tiwari, he has reduced my load by giving number of application his his slides. And as that Kundan has mentioned, my name, my designation, I don't have to repeat it. Now, when I wrote a book in 2016, there was something like travelology is going to play a major role in industry. And then what we realized something like we can save almost 5 trillion per year and by implementing the real travelological the procedures or science and maintenance procedures, whatever we mentioned. And then I realized at that time that many times books people are mentioning that Teflon or polymer coating or only the polymer is going to reduce the coefficient of friction and then maybe wear rate. We realize that's not correct. In some scenario it may be possible, but some other reasons we can even get a much lesser coefficient of friction. That's even a point not one also. Now we have achieved those things also in a laboratory using nanomaterials. So nanoscience and nanotechnology is very important to understand. And moreover, another thing is that we need to understand the physics and maybe say chemical structure at the nano level. At nano level, everything looks totally different. What we find on macro level, and yesterday in the BIS standard also, I was requesting, can you change RA value to RMS value? Because RMS value is going to change a lot. RA value is not going to give that kind of reliable results. So can we do that kind of things? And in my view, if you spend even the 50% amount on this kind of equipment, whatever we are assuming, but returns will come within 3 years itself. The spending our expenditure on this kind of activities will give you the much better returns. Now coming to the sustainable, because society is looking for all sustainable solutions, whether we need to really reduce the friction or not friction, but we require sustainable solution. We require something like a product which is coming out is going to should survive for years and years and years. And there the travelology comes in a top, the materials of science comes in a top. Then we require a mechatronics, because active element what Prof Tiwari has mentioned, that without mechatronics we cannot do those kind of thing. And in my view personally, because as I spent 6 years at the CMRI, I found without manufacturing excellence, whatever we do, it will be zero. So without really going for the excellence in a manufacturing, you cannot achieve those results. So we require a kind of a combination of all. One discipline is not going to really help. That's why I felt that industry participation is very important. Whatever we have done as a IIT level, TRL 3 or TRL 4 is more than sufficient for us, because we get a publication, maybe TRL 6, 7 we get IPS, but finally the industry has to accept it. It should go to industry. That's why I felt that is important to understand what are the really senses and then how we connect it. These are all important to make a smart bearing, and AMB or magnetic bearing is smart bearing only. We are going to that side. And of course yesterday we had a lot of deliberation whether the magnetic bearing is a part of the plain bearing or not, and I'm trying to give how to go with the cost economics, how to make this bearing as a part of the plain bearing itself in this case. Now this is what I took a traditional from a book. That's what we have learned in engineering when we start how to select a bearing. There are some sort of constraint, there is a speed constraint, load constraint, temperature constraint, and we select a bearing based on that. But we have beyond this, because every 5 years research is going to change a lot. So whatever the traditional 1985 things which we have been referring in the books are completely changing, and industry has a much more what is a response for that, because books we can teach, but industry demands we can improve those things also. These are important. That's why we say advance in the materials is important, production methods, control system, engineering approaches, all these are together going to evolve the bearings. If I take even example of the rolling element bearing, it started around 100 years back, and that they have developed, because I was in yesterday meeting, I was mentioning also, if I want to make a rolling element bearing at IIT Delhi, whatever the bearing 150 rupees you are selling, I'll take even the 15,000 rupees. Even that will not be sufficient. It will not be able to match the results. So research is something different, but it has to come to industry, and where a lot of research and the combination should be selected. So I'm just trying to give a very example of the rolling element bearing, which came in a Fortune Business Insight. It says that 2018, even it was USD, the overall projection was around $21 billion. And 2026, it will be $26.71 billion. This technology, 100-year-old technology, still has so much progress. Now, you start investing money in a magnetic bearing, I'm sure within 15 years, at least 10 to 15 years, we can replace complete rolling element bearing also. So this is what I'm trying to say. Reason being, we learn a lot through the exposure, right? I did one work in the Jindal Iron and Steel. That time I learned that the cage plays a very, very important role, because Timken companies are also here. I was studying their pin type cage, and Escape is also here, and then they were using the brass cage, and we found that brass cage is not efficient enough as a pin type bearings, a pin type cage. And we did analysis for that company, and we reported that the pin type is giving far better results. Even when you change a technology, everything changes. Even the way we need to fix, the way we need to locate, those things also change. It is not the traditional thing can continue with that. So we recommended finally our recommendations to the company, and they were very happy, and I don't know who become unhappy, I don't know, but the overall research went in bigger manner. Now I'm just trying to say, because many people have been talking, oh, magnetic bearing, so many complex circuits, wires, this, that. Now if you look at the rolling element bearing, the way they are manufacturing, now the bearing clearance plays itself a big role there. And this has been taught that bearing clearance comes in only in microns, which I can't do even in IIT now, the kind of manufacturing, right? You look at the clearance comes to something like lesser than 50 micron. Now, if I go with this kind of thinking, and I may say that if there's no standard, what will happen? If there's no standard, your alignment will not happen properly. Even the way assembly you want to make, it will not happen at all. I'll just give you the one example. If I have it's like a misalignment of 0.01 degree, it's not measurable. Unless there is a good standard and kind of equipment which we are going to use to assemble it. 0.10 degree, that gives a 5 micron misalignment itself. And if there is some bearing which has a 5 micron only internal clearance, whole internal clearance is exhausted. After that is only preloading. Now, if it is a 0.1 degree misalignment, it's going to create a more like a 50 micron clearance on the misalignment, which eats away complete clearance. The same bearing, which was ideal, the best bearing, it was performing well, just 1 degree misalignment creates a lot of problem. So same thing is happening with the magnetic bearings now. Whatever the problems which we are facing at the R&D level, that can be solved when the manufacturers or maybe industry can get involved on those kind of aspects. So this is, I'm just trying to show some results, and so if I simple try to connect with the force. How much force is coming because of this 5 micron misalignment? It gives something like a 42 kilonewton. I selected a bearing only for 5000 Newton load, and just 0.1 degree or 0.01 degree misalignment creates a 42 kilonewton load on that. Bearing can not work, will not work at all. And if I see the coefficient of friction, which are ideally supposed to be 0.0015, it becomes a 0.15, 100 times increase in a coefficient of friction. Right? So this is what I'm trying to say. When you think about magnetic bearing and you look at the future, and if you bring industry on the board, I think most of the problems of mag bearing, whatever we are facing, can be resolved, can be solved easily, and this technology can penetrate completely into our real world. Now, let's talk about some sort of, because this is the BIS related and then the invitation. So I had just written one lecture, the one slide only on standardization. I believe that unless we go for standardization, establishing the science, because I can make any bearing size, but what is really more suitable, we know the rolling element bearing comes with a standard size and we select. So don't give it too much freedom. You come up with some sizing, some tolerances, some sort of mounting interfaces, so that it is a two-way communication. Industry person also follows, user also follows, and the person who's designing that also follows. For time being, we don't have those standards at all. It's our wish, whatever we like, we want to design it, that we can experiment it. So that's important for us. Another one is interchangeability. If you buy Professor Tiwari's bearing from his lab and you buy a similar kind of specification from my lab, you will find a lot of change as such. Because we don't have those standards to keep fix those things, and then we will not be able to interchange. So that from that point of view, this kind of the fixing standards for magnetic bearings are very, very essential. If we want to really break this TRL 3 to 4, maybe we want to reach to the 8 and 9 kind of thing. Those are the standardization is very, very important for us. And then we need to also keep a check the power requirement, because otherwise we will not be able to solve the problems. Power requirement is essential. Even the efficiency is essential. You need to set those rules so that for time being we don't have any rules as such. If you set the rules, research will also move to those directions also. And then another thing, maybe I'll show the one slide. The newer and newer materials keep coming. Of course, India doesn't have those kind of materials. We have been importing. But again, there is a selection. Now, if there is a big demand, those materials will come much cheaper cost. When we buy a few materials or maybe a little bit quantity, it will vary significantly. And if I bring all those aspects, I find enormous application. I don't see any application where the magnetic bearing cannot be used. That's why the things of morning says, bearing is everywhere. So you can replace all the bearing with a magnetic bearing. How? I'll just show those kind of things in my, and the way you say that it requires evolving continuously with R&D, and then smart bearing, which is the foundation is coming, the ML, AI and all, those things can be implemented in this kind of magnetic bearing. So I believe if we R&D labs, institutions and industry work together, we'll surely see this kind of bearing into the market. And there are already applications which Professor Tiwari has shown. I'll be showing few applications, and then I believe that it will change completely. Now, number of questions came to Professor Tiwari, so I made this slide thinking that this kind of questions will come. You can see the kind of the load which magnetic bearing can see. So average we will say is a kind of a 0.05 megapascal on average pressure. More or less temperature should be lesser than 100 degrees centigrade, because otherwise the demagnetization will happen very fast. My efficiency will come down significantly. How fast demagnetization can be stopped by cooling arrangement or making some sort of additional arrangement, that's not possible. or which kind of materials really can have a high thermal conductivity, or the way we talked about something like a hybridization of with a hydraulic hydrodynamic bearings. So what kind of cooling agent, whether I will be using some sort of graphene nanoparticles to increase the thermal conductivity of the lubricant, of increasing the flow rate, those are possible. We can tune whatever is demanded, right? But ideally it should be lesser than 100 degrees centigrade, otherwise there will be problem. Of course, as I say, the application we can really make whatever you like, but again it should be customized, as Professor Tiwari has mentioned about the instability, or maybe say the control which really requires. So instability is an inherent problem in a magnetic bearing. But question comes, is it only the magnetic bearing? No, it's not. Gas bearing came much earlier than that. Gas bearing has much more instability compared to this. Here we are giving inverse power of the H2, that's a film thickness. While in think about a gas bearing, it's a cubic. That the sensitivity of the gas bearing is much more than magnetic bearing itself. So it's not only the magnetic bearing facing problem. Gas bearing has a more problem, but we have a solution for that. So if we have a solution for gas bearing, why not magnetic bearing? So this is another thing, and somebody who is designing magnetic bearing without thinking the gas bearing, that's absolutely wrong. Because when you go for the high, unless there is a vacuum, air will be there. There will be some sort of transmission, there will be some sort of sharing of the air. So without considering that, that's not possible for us to go ahead exclusively on the mag bearing. We need to account gas bearing or maybe air bearing into the account. So these are the things. While gas bearing, if you have look at the temperature, I can go sub-zero temperature, I can go to 2000 temperature also. Now, if I want to really design complete bearing only for the high temperature, I'll take a lead role, I'll give a lead role to the gas bearing and minor role to the magnetic bearing. So that overall good results, viable results can be obtained. Now, when I talk about the gas bearing, again, it has an enormous problem, but we have solved those problems, and I'm trying to show the analogy. Whatever we have done, same thing we are doing on the magnetic bearing with a new kind of garments to the magnetic bearing. Same thing we are doing exactly for the gas bearing, or maybe the magnetic bearing which we have done for the gas bearing. Now I find a similarity. We require excellent manufacturing, high precision. Even if I go with the nanometer level precision level, then only the gas bearing is going to work. Otherwise not. You talk of the foil bearing, you talk the bomb bearing, we require excellent precision in that. If without that, it is not going to work. And then as I say, the high speed application, gas bearings are more suitable compared to the magnetic bearing. And whichever way we want magnetic bearing to reduce the current which has been supplied, we may use the word AMB like a bias current, that can be reduced when we combine with a gas bearing. However, it has also the same load carrying capacity, low load carrying capacity gas bearing, and the magnetic bearing same thing. They have a worse damping. That's why when we design a gas bearing, we account those things also, and then fabrication cost is very high. Still, we are using gas bearing. It has been in mentioned in this manner. Now here, which the way gas bearing instability dealt, we do. Instead of the one single bearing, we make a multiple bearings. And exactly same thing we are doing with the active magnetic bearing. Instead of one active magnetic bearing, we are making 4 active magnetic bearing. We are making 8 active magnetic bearing, which Professor Tiwari has already shown the electromagnet. Whether you have 4 electromagnet, you have 8 electromagnet, what kind of control you have. Exactly same thing which we are doing. Which you have been doing with the gas bearing, we are doing with the AMB in this case. Now, I'm just showing one of the example. Even we do same thing with hydrodynamic bearing also. The 5-pad tilting pad bearing has been shown is a conventional being used extensively in a number of applications. Now, how we can really utilize this kind of technology for the magnetic bearing? That's possible because we already have a technology tilting pad bearing, and here you see the pad is getting adjusted. Right? In this case, otherwise what we do, we change the shaft, we adjust the shaft in AMB, while in this case we adjust the bearing itself, right? So it is a relative motion. I can adjust anything. Here the pad is adjusted, there the shaft is adjusted. We can really develop this one, I'll just take a very classical example. That's a hard disk drive. I don't know how many people know. The hard disk drive have an air bearing. And in 1985, enormous money was spent on that. Just to understand what is really happening in this hard disk drive. And simple, the data read and write head has to levitate from a disk. And this levitation is in nanometers. If I increase the space, then the disk size will increase. If I reduce the space, chances of wear will increase. So they use only layer thickness of 3 to 4 nanometer. And they use a read and write head and then levitate it and then operate it in 10,000 RPM also. Right? So these are the typical example where the 1985 onward the solutions are there. So why we are not combining this kind of solution? And this is what I'm trying to show the mechanism. So if you look at, this is what a taper roller, we have a levitation over here, and this is a air the bearing itself. And this operates maybe 6,000 to 10,000. 10,000 I have seen maximum in this case. Maybe I don't know recently whether it has a further enhance or not. But this is what things are available. Now how do we control air bearing? Same thing, the way we use magnetic bearing bias current, we use here the aerostatic. We pump the compressed gas, compressed air through the different vents. Now I can design those kind of vents. A compensatory it can be a different kind of thing. It can be ventry, it can be capillary. I have so many designs for that, exactly to match the results. Right, so these technologies are there. So magnetic bearing as such is not there. We are trying to utilize existing technologies, trying to implement in magnetic bearing so that the solutions are better and better. So somebody says it is a completely mechatronics. No, mechatronics is providing some tools to us, but our innovation, the way we think, the way we act, the way we actuate, they are traditional one or old one also. It's not that kind of much difference as such coming. Now if I compare also, if I compare the DN number, because in hydrodynamic and hydrostatic, DN number goes for the 100,000, while coming to the aerodynamic or aerostatic, it goes around 400,000, while in magnetic it's a 4,050 only, or 4,500. Sorry, 4,50,000 the DN number as such. So it's not really varying significantly from air bearing. Now that's why now come to the magnetic bearing. Already the Professor Tiwari has said the passive magnetic bearing, active magnetic bearing, that has been mentioned. Active magnetic bearing, he has demonstrated a couple of already application. So I'm not going to that. Only my experience with active magnetic bearing. We did a research in 2006. We made an active magnetic bearing. We compare, and then we compare initial cost as well as the running cost. And we found something like, it costs around $1,500. If I compare with the conventional bearing, that costs only $1,500. $15. That's almost 100 times less. Even the running cost, whatever the current we are providing to levitate the shaft, that came around something like a 48 watt. While we found the loss in bearing, and conventional bearing was only 7 watt. So we found that we really required some alternative, otherwise it cannot penetrate in the market. And particularly when we are talking about flywheel storage system, which requires an abundance, right? Because we want to eliminate the bearing from batteries from the market. Because the running cost, the battery is very high, replacement cost is very high, and as well as what will happen to that? Whatever the battery you are making, how it will be reconditioned, what kind of waste will be generated. So that's why the good solution which we can look for the storage device, flywheel storage device is the one which is supported on magnetic bearing. So that's why I'm going to present few slides on that. Now, minutes now. Okay, I'll just try to wrap up. So magnetic bearing, there are some sort of hidden facts. We assume that it will repel, and then we tried that this is a shaft inside in the bearing, and there should be levitation as such, and then because of the repulsion force, it should work. However, it works in both. One is a repulsion, other in axial direction it becomes attraction. and attraction creates a more problem. So whatever the bearing wear which we were not obtained and are not able to see in a conventional bearing, much more wear occurs in the permanent magnetic bearing. So that was something wrong. We need to change it. So that's why we change it. At the bottom we require levitation. From top we don't require that kind of levitation. So we recommended this kind of 180 degree and 45 degree arc, and we made the bearing. We published a paper also in IEEE. However, later we found that even little bit change, little bit disturbance is disturbing the bearing again. Right, and then we found that this kind of rotor, or maybe say the sleeve, the way Professor Tiwari has mentioned, we required a sleeve to be mounted on the shaft, and this is a 45 degree arc, and we found it really gets damaged. The shaft goes and hammers a magnet, and the magnet being a brittle, it comes in a fragment, and because of that, the complete polarity changes. Right, doesn't remain uniform. So you start one crack, that's more than sufficient to break complete bearing. Right, so that's why we require some other thing compared to that's what we were making, and that's why we started with the Halbach array arrangement. That's again in published literature. It's basically stacking up the small magnets, and so in that we get maximum radial force and minimum axial force. That's what we have done, and this is available in literature. The kind of polarization direction has been shown. We stack the magnet in a manner so that overall we get a more and more radial minimum axial arrangement. And I'm just trying to give an analogy. Same thing we do in the rolling bearings also. If you look at the taper one, anything, we go back to back arrangement. It can be X arrangement, it can be O arrangement, whichever manner you want. But we do a compensation this manner. That's the same thing which we are doing in a Halbach array. Then we made those kind of Halbach arrangements. We thought we are going to get a very good results, but unfortunately we did not get that kind of results. We again got a kind of wear of the magnets. Because reason being still some more thing was required, and that's what we implemented. And we observe also the demagnetization happens in a very quickly. The magnet, whatever the magnetic field initially, after a few rotation or maybe a few hundred rotation, demagnetization happens very spontaneously, and that creates a more problem. And in fact, it was a much lesser compared to the earlier full bearing. We are able to see here the disturbance is not that much high now compared to the full bearing, but still the damage happens, and then we need to change the magnet also. And you can see here initially the complete wear out was here, while in this case wear is happening at some places only. So that's why we started with a rotational magnetized direction arrangement. Halbach has had number of arrangement, so we had started working with RMD structure. It given very good results. Of course, it gives a more and more manufacturing difficulties to us. Now we need to make a magnet which is also radial magnetized, and we don't get so easily these magnets. We need to buy it. That's why I'm requesting industry to participate, so this kind of research can go in much different manner. We had a restriction of a 10 mm shaft, and when our theoretical calculations show that 10 micron will be a best option. So 10 micron, 100 micron making a permanent magnet is difficult for us immediately, but when the industry money comes and then they start working, I think solution will be there. And this is what I'm just trying to show the results. RMD gives a very good results compared to the other structure, and that's possible. Now if we try to do this kind of research, it will really help. We also did a hybridization with a hydrodynamic bearing, so you can see that instead of the wide span of the natural frequencies, or maybe say the frequency domain, now we get much narrow domain. Right? In this narrow domain, we should not operate the bearing, or maybe shaft should not be operated in this frequency domain. Other domain it's possible, because we are not getting that kind of disturbance. And whatever I showed, everything works only for one particular direction, maybe say load and speed condition. Whenever you change, you disturb, then things will not work. And when you require some reliable product, you need to keep disturbing again and again so that you get a best product in this case. So this is what we have done. And now, as I say that we really require thinner magnets that will give good results. We worked with N35 magnet. We have also a magnet of N50 we can procure and we can get a good results. And finally, we did a testing on this. We kept a very big flywheel. We could store energy. We could run for the number of hours. So this is working. But again, if you do little more disturbance, it will fail. But this is what a future for us. What do you say that at least from storage device, this is a foolproof. And then if industry will start participating, I think almost all the bearings can be replaced with this kind of bearings. So this is what my understanding. And now I was thinking about how to make a 10 micron, 100 micron magnet. 3D printers are available. Printed circuits can be done. I can combine AMB and a PMB together in a segmented manner, what we call a segmented manner. So that is possible with the 3D printing. That's possible. But how much really it will give results, that need to be tested. So hypothetically it is possible and it will provide a good results. Anyway, I'm just trying to show the last 2 slides. Many things which initially people thought it's not possible, I'm showing those are possible. Waste management I did in 2017 in Colony, like a CMERI, still that's working. We don't dump anything outside. And I have been informed now CSIR has given almost 25 crores so that it should spread to all CSIR lab. At least they should remain green labs. So I'm thankful that whatever I started in 2017, now after 6 years some results are coming. Now this mechanized scavenging system, again people thought in one way. We have been informed that our cabinet minister is also mentioning that CSR has made mechanized scavenging system. That because at least I have seen in my colony that time that most of the building are on a garbage and waste remains, water will remain there. And finally, that when we have a mob control related problems in Kashmir, so we made 3 vehicles. When I was taking this project, everybody felt that we cannot manufacture, we cannot develop, but this is what is possible. So everything, whatever is appearing today, not possible, will be possible with a consistent effort. Thank you for your attention.
Thank you very much, such an elegant presentations. So now this question answer sessions. If any questions from, yeah, please. Please. No.
Okay, only one question. Mr. Hirani, one question from my side, that as you are showing the more potential with respect to the present conventional bearings, what we are using it. So when you talk about the pressure, your slide, you have just mentioned the slide with respect to the pressure coming. The pressure should be very less, and the speed is at a maximum level. So how you can justify the existing bearings which are capable of taking high pressure with respect to this product?
Yeah. So when I started, it was starting like with the AMB, because if you go with more pressure, it require more bias current and more problem. That towards the end, when I came to the flywheel, those things were already overcome.
Okay.
When we were operating only in 10,000 RPM, we did not go to 25,000 RPM.
So if I talk about in terms of the newtons, if I talk about 10 kilonewton is there for the existing bearing.
Yeah, it can be tuned. As I say, now I have a permanent magnet, and I know that a Halbach arrangement can be made. And then if we, with industry participation, we can make a narrower magnet and stack up, we can increase the magnetic bearing capacity significantly. That's possible.
This is the last question.
Sir, is this useful only for the high speed and low load?
So sir, that started with AMB initially, what was presented. As I said, towards the end, and when I think about hybridization with other, all possibilities there.
Because the plain bearing generally runnings with the low speed and the high load is requirement is there.
So with the last towards, as I say, the hybridization, those things are possible. Now, what is a really plain bearing? In my view, again, I'm using only plain bearing. I'm changing the material. I'm changing the material of the sleeve, which is will be mounted on rotor. I'm changing the material of the bearing. That's only I'm doing. Remaining levitation is happening because of the magnetic force. Now, if you want to increase the damping of that, then you can add with the hydrodynamic action also. So your plain bearing plain bearing. Same groove arrangement, same water arrangement or lubricant arrangement, but much more load carrying capacity, no wear and almost zero friction. See, plain bearing, what is the problem? Initially, there will be friction, and the coefficient of friction goes 0.25, and the levitated condition is goes to 0.005, right? And because of the instability arise, while in this case, there's no touch at all. The levitation is inherently or always available. So coefficient of friction remains 0.005 to 0.005. Right? So that is stick slip phenomena which have been studying or oil wave that sir has mentioned, those things will completely get eliminated. Right? So that's what I'm saying, only magnetic, your plain bearing, I'm changing the material. If I want much more controllability or much more damping, or I say I don't want hydrodynamic at all, I'm more interested in mechatronics and sensors and smart bearing, then I'll go with a layer by layer structure. I'll remove hydrodynamic, I'll bring active magnet. Active magnet can be printed also, and then I supply very lesser current, because here the primary will be the magnetic bearing PMB based and secondary will be the AMB. Presently what is happening, AMB is a primary and the passive is a secondary. While what I was suggesting just opposite. See, permanent magnet has a much more potential. You make AMB as a secondary. And in a very close touch, or maybe because of some jerk or impact, shaft is going to touch. That time AMB will work.
Sir, I just want to ask one question, sir. Sir, I want to invite your comments regarding the reliability and the quality of power supply which needs to be used for this.
See, we generally go with a DC supply, whatever current we require. So whatever you are using the system there, that reliability of the system will be the governing factor. If the reliability of the system is very good, the AMB will have a good reliability.
Because, for example, when we use AC current, so
AC current we don't use in this.
okay,
We use DC current.
DC, but DC, that quality is there? any
Power
specific-
factor has to be very good then.
Yes.
Yeah, that's a one, almost one. So,
We can discuss it over the lunch.
thank you.
Thanks.